Stanford University.
The entropy of a probability distribution is the sum of all of the states. A probability distribution now means a probability for a system to be in the ith state, where now we really are thinking for the moment about states being discrete so that we can count them. Every state has a probability, P of I. Of course, where it came from, where that probability came from, we'll discuss later. But let's suppose somebody gives us, plops down for us a probability distribution P of I. Then there's a P of I. There's also an energy of I, the energy of the ith state. And the assumption now is that the sum of all the PI's is equal to 1. And pretty much a definition, the sum of P of I times E of I is equal to the average energy. It makes sense. You add up, you take all of the states, you add their energies, but weighted according to the probability of the ith state. And that's what's normally called an average quantity in statistics or in probability theory. I've never understood the difference between what statistics is and what probability is. I'm told by some of my friends who are statisticians that there is a difference, but I have never understood what it is. I think statistics are actually sets of data, aren't they? They're real data. Yeah, they're real data, right. But how a statistician is different than a probabilist, I'm not sure, I don't know. Anyway, I'll use the two terms synonymously, statistics and probability. And
they're probably the same.
They're probably not. They're probably not. But I'm not, right. Okay, so this one's more or less a definition, although a useful definition. This one is just sums of probabilities should be equal to 1. And entropy is by definition for a given probability distribution. It starts with minus, and then P of I logarithm of P of I. It looks like it's negative, but it's not. And the reason that all of the P's are less than 1. And for anything which is less than 1, the logarithm is negative. So this is actually a positive quantity. All right, so we discussed last time probability distributions and imagined that there was a one-parameter family of probability distributions. Here it is. Here's the next one. Here's the next one. And they may be plotted against the energy of the particular state. And they're parameterized by an average energy. Obviously, as the probability distribution gets broader and broader, or shifts to the right in some way, the average energy gets larger. There's a particular probability distribution, which is very special. It's 0 everywhere except at E equals 0, or E equals the minimum value, I should say, the minimum value of the energy. And that's, of course, the ground state of a system. The ground state of a system is described by a probability which is 0 everywhere except at the state of lowest energy, in which case the entropy is exactly 0. But as the probability distribution, as this one-parameter family of probability distribution shifts to the right, first of all, the energy tends to become larger, and the entropy tends to become larger, because the entropy is qualitatively simply a measure of actually the logarithm, but it's a measure of the number of states that are important underneath the probability distribution. And so as the probability distribution gets broader and broader, wider and wider, the average energy goes up, and at the same time, the entropy goes up. We will always assume that the entropy is a monotonically increasing function of the average energy. Now, of course, you can invent probability distributions for which that's not true. You can invent a probability distribution which gets narrower and narrower as it moves to the right. But, as we will see, the probability distributions that govern thermal equilibrium are not like that. We'll find out that exactly this picture is the picture that governs the probability distributions for the states in thermal equilibrium. Thermal equilibrium is characterized, you can characterize it by a temperature, of course, but you can also characterize it by an average energy. If you have a box of gas and you know the average energy in it, and it's in thermal equilibrium means that whatever was going to happen has finished happening, and now it's simply quiescent, and the molecules are all thoroughly mixed up and thoroughly dispersed throughout the system, and not much is happening, other than microscopically, of course. That's a state of thermal equilibrium. In a state of thermal equilibrium, heat tends not to flow. We will see, we'll understand that soon enough. Heat tends not to flow because all parts of the system are in equilibrium. And as I say, as we will see, the probability distributions for given average energy do in fact tend to broaden and broaden and broaden as the energy goes up, so that the entropy is a monotonically increasing function of energy. Important fact. Okay, we're going to go through now some of the laws of thermodynamics. The zeroth law, we'll talk about in a minute. The first law is just energy conservation. The zeroth law, in a certain sense, in an axiomatic sense, when people were axiomatizing thermodynamics, the zeroth law sort of came in before almost anything else. But today I think we think of the zeroth law as a consequence of the first law and the second law, in a sense. The second law of thermodynamics says that entropy increases. Now, what on earth does that mean? What it means is if you have a system described by a given probability distribution and it's not in equilibrium, right? When it's not in equilibrium and then it comes to equilibrium, generally speaking, the probability distribution broadens. We're going to prove that eventually. We'll prove it in a qualitative kind of way. We're going to qualitatively, we will prove the assertion that if you have a probability distribution and you allow it to evolve being a little bit careless, being a little bit careless is called fine graining, coarse graining, coarse graining. We'll find that the probability distribution always broadens, and that's not surprising. For a probability distribution to narrow, it means you found out more about the system than you originally knew. Typically, if you're talking about a very complex system of a large number of degrees of freedom, very difficult to keep track of, exactly the opposite tends to happen. You lose track of things. And because you lose track of things, the probability distribution tends to broaden, and that's the increase of entropy with time. All right, now, first law, energy is conserved. Second law, entropy always increases with time. If it doesn't increase, it stays the same, but it never decreases. Let's assume that the entropy always increases or stays the same. And now talk about the zeroth law. The zeroth law states basically, first of all, it asserts that there's such a thing as thermal equilibrium. that if you take a box, and let's talk about a box of gas, but it doesn't have to be gas. It could be liquid. It could be any system which is isolated and self-contained, that if you wait long enough, it will come to equilibrium. Now, what does it mean for it to come to equilibrium? If you imagine that the system is made out of separate parts, let's call them A, B, and let's put a third system in, C, and assume that they're connected. Connected means that they can exchange energy with each other. So let's put some little pipes between them that allows energy to flow between them. I'm not sure I like that picture. Yeah, it's okay. It's a good enough picture. That's fine. All right. What it says is that there's a concept called temperature such that the energy always flows from larger temperature to smaller temperature. That the energy flow is from larger temperature to smaller temperature, number one. And number two, it says, all right, so that's, sorry. It flows from larger temperature to smaller temperature if the system is not in equilibrium. But if you wait long enough, the flow will eventually come to an equilibrium. Let's suppose there's only two systems for a moment. Energy will flow from the one of higher temperature to the one of lower temperature. Until what point? Well, until the lower temperature one becomes hotter than the higher temperature one. But then the energy will flow back the other way. Well, that's not what happens. What happens is the energy just flows from the hotter to the colder system until they equilibrate. Until they equilibrate. Equilibrate, as we will see, means that the temperatures become equal. When the temperatures on both sides become equal, the heat stops flowing. That's kind of the meaning of temperature, if you like. The meaning of temperature is that it tells you which way heat flows. So number one, a notion of temperature exists such that heat flow, energy flow, is from the hotter to the colder. When the temperatures become equal, energy stops flowing. And if A is in equilibrium with B, that after all means that the temperature of A is the same as the temperature of B, and B is in equilibrium with C, that means that the temperature of B is equal to the temperature of C, then obviously the A is in equilibrium with C. That just says if the temperature of A is the same as the temperature of B and the temperature of B is the same as the temperature of C, then the temperature of A and the temperature of C are the same. So you can sort of summarize the zeroth law by saying there's a notion of temperature, which we've already introduced, but we're going to use it to illuminate this law. There's a notion of temperature, and, number one. Number two, energy flows from higher temperature to lower temperature. And number three, in thermal equilibrium, the temperature of all parts of the system is the same. If the temperature was not the same in all parts of the system, energy would flow until it became the same. That's the basic zeroth law. The existence of a temperature function that tells you which way energy flows, and the existence of an equilibrium when the temperature in all parts of the system are the same. All right, so let's see if we can relate those ideas to the notion of temperature that we introduced earlier, last time, namely that temperature is related to the derivative of energy, or the change in energy with respect to entropy. If you change the energy a little bit, the average energy this means, if you change the average energy a little bit, the entropy will change, and that derivative, that rate of change, is called the temperature. Let's see if we can see what this definition of temperature has to do with the idea of the flow of heat and which way it goes. So let's begin. Let's take a a system composed of two parts. Let's call it A and B with a little pipe between them. And let's write down all the basic equations that we know. But before I start, for the moment, let's assume that the temperature of B is bigger than the temperature of A. Now, if the temperature of A is bigger than the temperature of B, just switch them. Just interchange A and B in everything I say. Okay, but we have to pick one. Of course, we could have the temperature of B equal to the temperature of A, but let's take the case where they're not equal, and that means they're not in equilibrium. They're not in equilibrium. The temperature of B is bigger than the temperature of A. Okay, so let's write down some equations. The first equation tells us that when the system responds and does whatever it's going to do, the total energy doesn't change. Now, what is it going to do? What it's going to do is there's going to be some energy shift from one to the other. All right, so let's say the change in the energy of A plus the change in the energy of B, when whatever happens, happens, in other words, after a small amount of time, that is equal to 0. We take our stopwatch, we wait 1 second, and we look how the energy redistributes itself. We find out that the energy of A changes, we find out that the energy of B changes, but energy conservation tells us that the sum of the energies doesn't change. Next, the change in the entropy of A plus the change in the entropy of B, that's the change in the total entropy, in fact, that is always greater than, once in a while it's equal to 0, but only in very special cases. The general statement is that it's generally greater than 0. The change in the entropy of A plus the change in the entropy of B, which is the change in the total entropy, the entropy of the whole system. In other words, the probability distribution of the combined system, the probability distribution of the combined system shifts in such a way as to make the distribution broader. That's what it says. Okay, now let's use one more statement, that the change in the energy is equal to the temperature times the change in the entropy. And let's apply this to both A and B. dEA is equal to the temperature of A times the change of the entropy of A, and same thing for B. Then we can rewrite this equation over here, this is the first law of thermodynamics now, as TA dSA plus TB dSB is equal to 0. Or just to write it in a form which is somewhat more useful for me, I'm going to solve this equation for dSB. I'm going to solve it for this guy over here. And what do we get? We get that dSB comma dSB is equal to minus, because I'm going to transpose this term to the right-hand side. That will give me a minus, TA, but now I have to divide by TB, dSA. And now take this formula and stick it into here. You know, as usual, I always tell people, to do physics, you first think really hard about what you want to do, and then you blindly just go ahead with the equations and see where they lead. All right, so we have SA and SB, DSA, DSB, but they're connected, so let's eliminate one of them and rewrite this inequality. So we rewrite the inequality. It's DSA plus, but now it's minus because dSB has a minus sign in it, minus TA over TB times dSA, and that's greater than 0. That's what the second law tells us. Allow me to multiply it by TB for simplicity. Let's just multiply it by TB. We will assume temperatures are positive unless otherwise. There are situations in which temperature can be negative, but not for us for the moment. So what does it say? It says TB minus TA, let's write it out, TB minus TA times dSA is greater than 0. Now, we've already assumed that the temperature of B is bigger than the temperature of A. We can also look at the other case, which we'll do in a moment. But if the temperature of B is indeed bigger than the temperature of A, then TB minus TA is positive. What does that say about dSA? A positive number times the change in the A entropy is positive. That says that dSA is positive. Okay. So, what we conclude from this equation is that dSA for the particular setup up there is greater than 0. Now, what would happen if TA were bigger than TB? Exactly the opposite. Then TB minus TA would be negative, and dSA would be negative. But we've already chosen our convention. We've decided to call B the one with the bigger temperature, and in that case, dSA is bigger than 0. Let's just multiply this equation, or this inequality, by TA. TA times dSA is bigger than 0. But what is TA times dSA? It's the change in energy of the subsystem A. This is D of the energy of A. So what have we found? By a little bit of manipulation and the use of a couple of laws. What are the laws? The first law, energy conservation. The second law, entropy increases. And that's all we used, plus a little bit of juggling of and transposing and multiplying by simple algebraic operations. We find that the change in the energy of A is greater than 0. It follows, of course, that the change in the energy of B is less than 0. In other words, heat has flowed, or energy has flowed, from B to A. So we have proved that with the definition of entropy, the definition of temperature as given here, that the temperature is such that it defines a direction of heat flow. Heat will flow, and when I say heat, incidentally, I just mean energy. Energy will flow from B to A until the temperatures become equal. When the temperatures become equal, of course, if TA equals TB, then there's no flow. That's easy to see. And that's when equilibrium is established. So equilibrium is established, or there will be no flow of heat, when TB equals TA, then there's no flow of heat altogether. Okay, so that's the zeroth law of thermodynamics, namely, the temperature determines the direction of heat flow. When the heat flow stops because the system comes to equilibrium, it must be that the temperature is the same in every part of the system. Conversely, if the temperature is not the same in every part of the system, heat will flow until it is the same.
Question.
Yeah.
So it seems, this analysis seems to assume that system A and system B individually are in equilibrium. So it's like a...
Yeah. That is true. That is true. That is true. But if they're not in equilibrium, it could be because when you break it up into smaller subsystems, the smaller subsystems are not in equilibrium with each other, and then you just apply the analysis to the subsystems. Right. Good. Yeah, so that was correct. I did imagine that system A and system B separately were in equilibrium with themselves, so to speak. So that's a good point. All right, now we come to the hard question. Yeah.
Just so I can have something specific in mind here, when we talk about states, should I think of this whole picture here with the, like we've got a gas in there?
Mm-hmm.
Should I think of the state as being the position and the velocity or momentum of every single molecule in there?
Yes, except that in quantum mechanics we can take those to be discrete variables, basically. Yes, that is. Or we simply substitute for S an integral instead of a sum. Yeah, but that's what, yes. Look, a state always means the same thing. It means as much as you can possibly know about the system if you were infinitely powerful. Now, there may be limits that have to do with the fundamental rules of physics, such as quantum mechanics, which tells you you can't know as much as you thought you might have liked to know, such as the position and velocity of every particle. But still, a state means as much as can be known about a system by, let's call it, an infinitely powerful observer.
Now, there's a finite number of particles in there, but their velocities and positions are not discrete. So
In quantum mechanics, they are. Yeah, in quantum mechanics, they are. So in quantum mechanics, the state counting for a finite box is discrete. Yeah. What we're going to have to show is that if we do the correct quantum mechanics, statistical mechanics, then in a certain limit it becomes equal to the classical statistical mechanics. In other words, in a certain limit you can replace sums by integrals. That's what it comes down to. And that's a subtle business. That's not a one-liner. That's a subtle business, but it is true. All right, so now the next question, the open question, is in equilibrium, after equilibrium is established, you have this box of gas, or whatever it is. There's some probability distribution, P of I, for the system to be in its different microstates. What is that probability distribution? What's the mathematics of it? So that's what we're going to begin to study now, and right now. First of all, it's always a useful idea, not only useful, it usually corresponds to the facts, to imagine that your system that you're interested in is not closed, but is in contact with the outside world and can exchange energy with it. In particular, it's a useful idea if you want to think about the probability distribution of the states of this subsystem, to think of it as being embedded in a huge reservoir of a much larger number of degrees of freedom that provide a heat bath. Which allows energy to flow back and forth until the system in question comes to thermal equilibrium with the big heat bath. The heat bath is so big that if even a little bit of energy flows from into the subsystem, the temperature doesn't change much. Now, this is something we could also prove, but just think about it for a minute. We have a big, huge system at a certain temperature, and we have a little system, and a little bit of heat flows from the big system to the little system. typically the change in the temperature will be, of the big system will be negligible. And so we can imagine the big system is at some temperature and simply wait until the small system is in equilibrium with the big system. Now, a particularly convenient choice of heat bath, you'll see why, but a particularly convenient choice of heat bath, which often actually corresponds to the facts, but a particularly interesting choice is just to imagine that the system in question is one of a very large number of identical systems which are connected together by little pipes that allow heat to flow back and forth. One of them is the system that we're studying. The rest of them simply provide the heat bath. Actually, this sometimes corresponds to the more or less the facts. In particular, if we have a very big system and we divide it into small subsystems, the small subsystems may be very much alike, and the big system then is just a heat bath, and the small subsystems just provide a large number of replicas that all together add up to the big system. So this is a useful trick to pretend that the heat bath is just a repetition of the same system over and over again. How many such subsystems? Well, eventually we're going to let them get a large number of them, large enough that we can think of the heat bath as very big. But let's call it capital N for a moment. That's the number of these systems we have. And now each one of the systems is in a state. All right, so here's my demonstration. These are the identical systems. What do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9. So capital N is equal to 9. These are the possible states. These are all identical, so I'm not going to do anything to them. But of course, the states of the system are not identical. They have different energy, for example. So let's color them to remind ourselves that the states are not all alike, and in particular that they have different energy. The states are not real systems. The states are just labels, sort of, or not labels, but. And some of the systems are going to be in one state. Some of them are going to be in the other state. And some of them will be in the third state. Here's a particularly simple example where there's only 3 states. Each state has different energy. The energy might increase from right to left, your right to your left. No, your right. My right to my left, your left to your right. The energy increases in one direction. And what I want, we're going to call the number of systems, subsystems, in the ith state. All right, here's the ith state. Let's draw the states. I'm just going to indicate them by an axis here. Could be the energy axis. And these are all the possible states of the system. This is I, and the states will be labeled by I. I equals 1, I equals 2, ... And there might be an infinite number of states. In fact, in general, there will be an infinite number of states. Most of them have so much energy that there's no chance at all that they're going to be occupied. Okay? So there will be a negligible number of subsystems, or a negligible fraction of them will occupy enormously high energy states, just because we may not have that much energy available. But now let's introduce the concept of an occupation number. An occupation number is the number of systems, in this case it would be 3, occupying the ith state. In this case, the red state or the ground state, the lowest energy state. And we'll call that little n sub I. All right, here's I. And this is the number of our replicas here, which are found in the box labeled I. The box labeled I just means that the system has that particular state. And what we're interested in, for statistical purposes, for probabilistic purposes, is we're interested in how many ways are there of redistributing the systems among the states for a given set of n sub i's. N sub I here stands for n1, n2, n3, n4, and so forth. All right, so there are these occupation numbers, and the question is, given the occupation numbers, how many ways are there of redistributing the states so as to create that set of occupation numbers? Obviously, that's going to be closely connected with the probability for given values of the occupation, for probabilities for the state I, or for the occupation numbers n sub I. The more ways there are of distributing this system into a given set of occupation numbers, the more likely that set of occupation numbers is. That's a symmetry argument. If all possible ways of redistributing things are symmetric with respect to each other and equally likely, then the most probable configuration, which means the most probable set of occupation numbers, is the set of occupation numbers which gives rise to the maximum number of ways of redistributing things. So let's do some simple examples.
Is there an energy constraint, or these are all?
Yeah. Right. All right. Right. We're going to come back to that. There is an energy constraint, so let's write the energy constraint. All right. Since you ask, I had intended to come to that later, but since you ask, on top of the probability distribution that's associated with this different number of ways of redistributing things, there are constraints. The first constraint, let's write the first constraint. The first constraint is n1 plus n2 plus n3. This is the number of systems in the first level plus the number of systems in the second level plus the number of systems in the third level, or just ... or just the summation over I of n sub I is equal to what? Capital N, total number of systems. Now there's another constraint, which is the one that was just asked about, namely the total energy of the system. So let's write that constraint. The number of systems in the first state times the energy of the first state plus the number of systems in the second state times the energy of the second state altogether plus ... That, of course, is equal to the summation over I of n sub I e sub I. What is that equal to? The total energy, right? Now, let's assume that the total energy is proportional to n. We're going to be studying this system, making more and more replicas, okay? But it's clear that as we double the number of replicas, the total energy will double, at least if we want to keep things fixed within a given box, and we do. So we can expect that the total energy is equal to capital N times the average energy per box. Let's just call the average energy per the boxes now. I use the word boxes. Forget boxes. The average energy per subsystem here is E, and the total energy is capital N times E, and that must be simply the sum of all the energies. Okay, so before we move on to some probabilistic things, let's just rewrite this in another way. If I were to tell you that the occupation numbers were N1, N2, N3, and so forth, and the total number of systems was capital N, and then ask you, what is the probability that a given one of these systems is in the ith state, what would your answer be? Well, I think we'd all come to the same answer. The answer is the fraction of systems that are in the ith state. A good definition in this context of the probability that any one of them is in the ith state here is simply the ratio of the number of the occupation number n sub I to the total number. That's what a probability is in this context. So let's define the probability that any one of these boxes or any one of these subsystems is in the state I to just be the fraction n sub I, which is the number of them in the state I, divided by the total number.
Is n I the same as n sub I?
Yeah. N of I is the same as n sub I. Good, thank you. That's the way we normally use probability. Probability is a measure of the fraction of, the expected fraction of events of a given type. In this case, the event is measuring whether a system is in the state I or not. Okay, so P sub I is n sub I. Now supposing, let's now use this to rewrite these two constraints. These are two constraints. One says that the total number of systems is capital N, and the other says that the total energy is equal to capital N times the energy per system. All right, so if I do that, I can then let's rewrite this. P of I times N is equal to Ni. And what does this become? This becomes the summation over I, N times Pi, that's just Ni, little ni, is equal to capital N. And now divide by capital N, and what do we get? We get the sum of P sub I is equal to 1. That should surprise nobody. Okay, that should surprise nobody. But it's just another way of writing the constraint that the total number of systems is equal to N. And what about this equation here? This becomes summation over I of N times Pi is N times the total energy. And again, divide by N. And it says what we knew all along, that E on the right-hand side is just the average energy of any one of the systems. Okay, so these are two good things to remember. These are two constraints, and whatever the probability distribution is, the probability distribution is some P of I, whatever it is, it has to satisfy these two constraints, average energy and total probability. Or if we want to think about it in terms of the occupation numbers, well, you can rewrite it in terms of the occupation numbers. Okay, but before we worry about the total number of systems being kept constant and the total energy being kept constant, let's just ask a more primitive question. For a given set of occupation numbers, N1 through N, however, infinitely many of them, how many ways are there of redistributing our systems to correspond to that number? So if you know anything about combinatorics, you know the answer. But, and And I'm not going to prove the answer. This is this is probably the hardest mathematics in this course. I always find combinatorics very tricky. But there's a small number of rules. And I'm not going to go through them. I'm going to tell you the answer, and then we'll just check it for a couple of cases. We'll check it for a couple of cases, see that it really is true. OK, so we have a set of n's. Now, clearly, if capital N is finite, and let's assume capital N is finite, maybe very big, and we're interested in the limit in which it really is very big. But for the moment, let's take it to be finite. And let's also suppose there's an infinite number of energy levels that go up to the sky. Most of the occupation numbers are going to be 0. Keep that in mind. Most of the occupation numbers are going to be 0. All right, the answer is the number of ways, I don't want to, let's see, let's just write it out. Number of arrangements, let's call it. Number of ways of in order to keep the occupation number fixed, the set of occupation numbers fixed, is n factorial, the total number of them factorial, divided by the product n1 factorial, n2 factorial, n3 factorial, dot, 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 all of them. In other words, capital N factorial divided by the product, this is the symbol for product over I, of n sub I factorial. We're going to check it for a few cases, make sure it's true. But this is a combinatoric fact. But first of all, what about all the ones which are 0? Don't they give us zeros in the denominator? No. Why not? 0 factorial is 1. So all the ones which are unoccupied, just give us 1 and we can forget them. All the occupation numbers which are 0 contribute the factor 1 for each one of them. So there's no danger of this thing blowing up because there are a lot of n's equal to 0. 0 factorial equals 1 factorial equals 1. Now, we could use mathematical induction to prove that every number factorial is equal to 1. That makes things simple. Yeah.
It's a unified field theory, huh?
That's right. Okay. Just in case you think I'm not, I'm serious, I'm not. 2 factorial is 2.
Oh, one question. In reality, in general, there will be more than one set of occupation numbers that satisfies the constraints.
Oh, yes. Oh, yes. There are lots of ways of, that's what we're counting. We're counting how many ways. No, for the moment, forget the constraints.
This is the number of arrangements for this fixed set of occupation numbers.
This is the number of arrangements for a fixed set of occupation numbers with no regard to whether the constraints are satisfied. We will come back to the question of the constraints being satisfied. We will have to add on top of this the effect of constraints. All right? But let's just look at this for a moment and study it. It's an interesting expression. We're going to want to approximate it. Oh, let's check it for a couple of cases.
It does feel appropriate to do this on April 15th. Tax day.
Yeah, I know, but why?
Oh, it's 1040 and all the rules, so.
Is 1040 a factorial?
Computations.
Okay. Right. Okay, let's just check it for a couple of cases. First of all, supposing you take all, supposing we're interested in the case where one of the occupation numbers is capital N and all the other ones are 0. All right? That would say one of these is n factorial, all the others are 1, And it's just n factorial over n factorial, which is 1. Well, that seems reasonable. How many ways are there of putting all of the things into one cup? 1. Okay, good. Let's try a couple of simple cases. Let's suppose we have two subsystems, and we want to know how many ways are there of putting 2 of them into one cup. Well, we've already done that. That's one way. That's the other possibility is 1 in one cup and 1 in another cup. Okay. All right. Let's first check the answer this way. All right. There are 2 systems. So there's 2 factorial, and each cup now, this is the first cup and the second cup and the third cup. The first cup has 1, the second cup has 1, and the third cup has 0. So this is 1 factorial times 1 factorial times 0 factorial, which is 1. So the answer is 2 factorial, or 2. 2 ways of putting 2 systems into a given pair of cups, with the other one being empty. And of course, that's true. You can put this one here and this one here, or you can put this one here and this one here. 2 ways. Let's do one more case. First of all, how many ways are there of taking 3 subsystems and distributing them into 3 states, no 2 the same? That's not as obvious, is it? Anybody got a quick answer? What? Yeah, it is 3 factorial. Yeah, it's 3 factorial. What is it? It's according to this, there are 3 systems, so that becomes 3 factorial over 1 factorial, 1 factorial, 1 factorial, which is just 3 factorial, which is 6. And in fact, there are 6 ways. But you know how to do it. You know how to do it. And in general, this is the formula. This really is the formula. You can prove it. It's not too hard to prove. Or you can just go look up in a Combinatorics book, the proof. High school, I think this is done in high school, if I remember. I don't remember, but. Okay, so this is the number of ways of taking capital N things and distributing them among the possible states with occupation numbers N1, N2, and N3. Now what we're going to find is that in the situations we're interested in, this can be thought of as a function of the N's, a function of the occupation numbers. And in the circumstances that we're going to be interested in, we're going to find that the things like this are highly peaked at a particular set of occupation numbers. Namely, when capital N gets very, very big, we're going to find that the occupation numbers cluster very, very strongly about a particular set of occupation numbers, or better yet, a particular set of fractions, little n over big N, that distribution gets tighter and tighter as n gets up, so that the probabilities little n over big N are well defined. Okay, so now let's do a little. In order to do that, we have to have some approximation methods. And the first thing we need to approximate is factorials. When I say approximate, I mean approximate under the circumstances that the n's are all very big. Here's what we imagine: that we simply allow the number of subsystems to get bigger and bigger and bigger in such a way that the occupation numbers also simultaneously get bigger and bigger and bigger. So all the n's are going to be assumed to be very big. And let's approximate this. Let's approximate this using a standard approximation for factorials. Everybody know the name of the approximation? Stirling's approximation. All right. Shall we prove it? Let's prove it. Let's prove Stirling's approximation. If everybody knows how to prove it, then I won't prove it. But raise your hand if you know how to prove Stirling's approximation. You will be called upon to do it. I noticed Michael's hand went back down when I said that. But I'll bet that he does know. That's another. Raise your hand if you know what Stirling's approximation is. Raise your hand if you don't. Okay, so good. So we do Stirling's approximation. Good. All right. First I'll write out what it is, and then we'll prove it. N factorial, as n gets larger and larger and larger, becomes better and better approximated by the number n to the, I'm running out of ink here. Let's see. Yeah. N to the n times e to the minus n. Now, there are all sorts of corrections to this which become important when n is not too big. But the bigger that n gets, the closer this gets to being correct. All right, so let's see if we can prove it. Let's take n factorial, and in order to prove it, what we're going to do is work with the logarithm of the function. We're interested in n factorial, but instead we'll calculate logarithm of n factorial. Now, n factorial, of course, this is an approximate equality. But what is n factorial? N factorial is 1 times 2 times up to n. And the logarithm of n factorial is log of 1 plus log 2 plus dot, 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 up to log n. Log n. Or in other words, it's the sum of log, let's call it x for the moment, sum of log x, where x is an integer, from, we might as well take it, we can take it from 1 to capital N. We add them all up, and that gives us the logarithm of n factorial. Okay, so log n factorial is a sum, I've written it there, a sum from, we can take it from I equals 1. We could also take it from I equals 0. It doesn't matter. When n gets very large, it doesn't matter exactly where we begin the sum. But from I equals 1 to n, logarithm, oh sorry, from x equals 1, log of x, where for the moment x is a integer. Okay, so we can draw a picture of this. Logarithm, here's 1. Logarithm is a function which looks like so. This is x. This is log x. It grows forever and ever, but at ever progressively smaller and smaller rate. And now we want to add up all of the integer, all of the logarithms at all of the integers, starting at 1, 2, 3, 4, 5, 6, and so forth. The distance between the integers here, of course, is just 1. Different integers are integers after all. And it's kind of obvious that you can make as a first approximation, and this is the approximation we'll make. The first approximation is to say this is just given by the area, adding them all up, with a small error. And the error can be estimated. It modifies the formula a little bit. But we can add all of this up and replace it to a good approximation by the integral. Is to a good approximation, particularly when n gets large, the integral dx of logarithm of x. From where to where? From x equals 1, where log x is just 0, to capital N. Okay. So all we have to do is learn how to compute the integral of log. rather than bat our heads against the wall and try to compute the integral of log x, let's take the answer and differentiate it and see that it really does give log x. Go in the opposite direction. So the integral, just the indefinite integral of log x, is x log x minus x. Let's check that. How did I know that? I know it because I once by trial and error, a little bit of trial and error, and you can make your best guess, and this is it. Okay, all we have to do is differentiate this, differentiate what's in here, and show that it's log x. Okay, so first of all, the derivative of x log x, you first differentiate x. This is, the derivative of x is just 1, so that gives you log x. That's what we want. And then x times the derivative of log x. What's the derivative of log x? All right, so the derivative, so good. So x times the derivative of log x is just 1. What's the derivative of minus x? Minus 1. So there we are. We have proved that the integral, well, d by dx of this thing here is log x, or the integral of log x is x log x minus x. So there we go. The integral of this is x log x minus x evaluated between x equals n and x equals 1. All right, now at x equals 1, this just vanishes. So we don't have to worry. X vanishes, log x vanishes, it all vanishes. So the whole answer is n log n minus n. We have now computed, to a certain approximation, we've now computed logarithm of n factorial, and it's equal to n log n minus n. How do we find n factorial from this? If we know the logarithm of something, there's a certain operation we do to it to find the thing itself. Exponentiate it. Exponentiate it. Okay, so the exponential of both sides, the exponential of the left side is, of course, n factorial. The exponential of the right side is, first of all, the exponential of n log n, and then e to the minus n. The exponential of a sum is the product of exponentials. In this case, the exponential of a difference is the ratio of exponentials, e to the n log n times e to the minus n. Did I write down Stirling's formula somewheres? Where? Oh, here. All right, we've located e to the minus n, but if you spend a minute or two, you'll see that e to the n log n is the same as n to the n. I'll leave that to you to prove. The easiest way to prove it is to prove that the logarithms are the same. The logarithm of e to the n log n is what? N log n. What's the logarithm of n to the n? N log n. Good. So here we have it. Here is our Stirling's formula, or our Stirling approximation.
Excuse me. Not that it matters that much, it's just a little factor, but you need a plus 1 down there. The x log x minus x1 evaluated at 1 is...
Yeah. There's a, right. There's a, there is a little discrepancy here, but it doesn't matter as n gets big. As n gets big, it's negligible.
More important than that is there's a factor, square root of n, that's missing.
Yeah. It comes from all these little pieces here. Yeah, but square root of, Right, there's an infinite number. There's an infinite number of, if I remember, I think the square root of n comes from some approximation where you replace these by straight lines, but you're still missing a little bit. There's an infinite number of factors, but
Well, if you include the square root of 2 pi, you're going to get close enough to give you the integer results.
this, I assure you, this is close enough here. Yeah, this is close enough for our purposes. And, work out 100 factorial and try it. It's not too bad. The convergence is actually slower than I thought. I once worked it out for a couple of first 20 or so. It was not as fast as I thought, but it does converge pretty reasonably rapidly. And for 10 to the 23rd, it's an awfully, it's plenty good, which is the number of atoms in a mole. Okay, so here's our approximation, n to the n e to the minus n. And that's all the other subleading factors cancel. They're not important, and we can do that right here. Okay, so now let's take this monstrous combinatorial coefficient here, and that's what it's called. It's combinatorial variable. Remember what it is. Remember, keep in mind what it is. It's the number of ways of rearranging capital N things into little n states. What we're going to do with it, incidentally, is we're going to maximize it. We're going to look for the set of little n's, which makes the number of ways of rearranging as big as possible. That's what we're going to do. We're going to look for the set of little n's which makes this as big as possible. The fact is that we will find a very sharp function, but not yet. We're not there yet. So first we need to deal with this object here. Okay. What I'm going to be interested in, I'll tell you now what we're interested in. We're going to want to maximize this, but subject to two constraints. The two constraints are the constraints we wrote out before, namely that the summation of n sub I is capital N, and the summation of n sub I e sub I is a fixed number e. What we'd like to find out is what is the set of occupation numbers which makes this as big as possible, given that the sum of the n sub i's is capital N and the sum of the energies is E. That's the mathematical problem we want to work out. Once we've found that, then we effectively know all of the probabilities through this equation here. Once we know these little n's, the occupation numbers, then we know the probabilities. Okay, the first thing to do is to say we have a product. We have a big product. How do you maximize a thing, incidentally? You differentiate it. Differentiate it with respect to what? The little n's. Now, the little n's are not continuous variables here, but in a little while they'll become pretty continuous. But we have a big product, and to differentiate a big product is more of a nuisance than differentiating a sum. All right? Well, we want to maximize something, but maximizing it is the same as maximizing its logarithm. You can maximize a function by maximizing its logarithm. If you found the place where the function is biggest, that's also where its logarithm is biggest. Logarithm is a monotonic function, and so wherever the function is biggest, its logarithm is also biggest. So let's take the logarithm of this, log of n factorial, the log of the target function here, product of n sub I. That's equal to the log of n factorial. I'm sort of, what I'm doing a bit is going backward, but I've, yeah. Ooh. No. I forgot. I wanted to use Stirling's approximation. Before we do this, let's use Stirling's approximation. Okay, let's use Stirling's approximation before we go ahead. Okay. What is this? This is equal to capital N factorial e to the minus capital N. N times to the power of n. Not n factorial. N to the n. That's what I wanted. N to the n e to the minus n. And then downstairs, n1 to the n1. Now there's e to the minus the n1. Let's put that over here. E to the minus n1. Then there's n2 to the n2, e to the minus n2. There's n3 to the n3, e to the minus n3, minus n3, and so forth. All right, now let's use the fact that we know that the sums of the n's have to add up to capital N. Then e to the minus n1 plus n2 plus n3 and so forth is just e to the capital N. So those factors cancel. This and this cancel. And in fact, all the other subleading things that have been not quite calculated carefully enough, they also cancel. And we now have a nice expression that the number of arrangements to a high approximation is n to the n, capital N to the n, divided by the product of n sub I to the n sub I. Now let's take its logarithm. There's a lot of these steps are not very hard. The story is longer than it really needs to be, but let's take its logarithm. Okay, so let's call it C. C for combinatoric. What is the log of C? That's equal to n log n, that's this one, minus the summation over I of n sub I log n sub I. Now you might start to smell something interesting here. Maybe not, but I do. Let's go back and remember that the little n's can be interpreted as probabilities. This is looking awfully interesting here. It doesn't quite look like p sub I log p sub I, but it's somehow related to it because the n's are related to the p's. And what is the sum over I of p sub I log p sub I? The entropy. The entropy if the probability distribution really is given by this. So let's carry this out. Let's carry this out, the steps out, and see that in fact that what we're doing is actually maximizing and trying to maximize the number of ways of rearranging the coffee packets here. What we're doing is maximizing some entropy. We're finding the probabilities which maximize the entropy under certain constrained circumstances. Okay, so let's just take this and let's take this over here. I'm going to pull it over to here. Log C is equal to n log n minus summation over I of n sub I log n sub I. And now plug in that little n sub I can be identified in terms of the probability p sub I times the total number of things. All right, so let's do that here. This is n log n minus summation over I. N sub I is p sub I times capital N, right? But what about log n sub I? That's log of p sub I times n, right? But log p sub I times n is log p sub I plus log n. Okay, let's take the second term first. P sub I n log n. Notice that the n's that appear here, the big n's, those aren't functions of I. They're just n, whatever n is. What is the sum over P sub I? 1, right? So if you look carefully at this, you'll see that the second term here is n log n times the summation over I of P sub I. Summation over I, P sub I, times n log n. But what is the sum of P sub I? It's just 1. So the first thing we find is that this n log n cancels this n log n here. Why? Because the sum of the P sub i's add up to 1. So we can forget this. We can forget this. Take the n on the outside. And what do we have? We have capital N, the total number of systems, times the entropy of any one of the systems. Remember, the P sub i's now are the probabilities for a given system to be in the state I. So apart from this factor of n, which is just there because there are n subsystems altogether, what we're going to be asking about is maximizing the entropy. If we want to find out the occupation numbers which maximize the number of ways that you can rearrange the system, keeping the occupation numbers fixed, it simply corresponds to maximizing the entropy. That may or may not be surprising to you. If it's surprising to you, good. It's a pleasant surprise. If you know it, you know it. Okay. Yeah.
If you look at the formula itself, just from pure arithmetic, n factorial over the little factorials. That.
Wait, say it again. Say it again.
That one, n factorial over the product of.
Yeah.
That would be maximized if all the n's are equal, the little ones.
Yeah.
What's the meaning of it?
It means that the most probable situation is just to what it means is that all occupation number distributions are equally probable. But we have to add something important. We have to add the constraints. What we're trying to do is maximize this, but subject to 2 constraints. The first is that the total numbers, the sum of the n's, is all equal to capital N. And the second is that the total energy is fixed. Then it's no longer true that the thing which maximizes it is uniform.
Mostly because of the energy.
Both are important. Both are important. Both are important. Yeah.
When you use Stirling's approximation, it made sense for the numerator because capital N is large, but do we need to justify using it in the denominator?
Mm-hmm. As capital N gets large, the little n's will get large in the same proportion. If you double the total number of systems, every average occupation number will also double. So I suppose what you have to do to really do this honestly is to chop this off somewhere and say, look, I know that I don't have more energy than a certain amount, and ignore everything above some point, and then start making capital N bigger and bigger and bigger, and all of the important contributions will come from little n's, which also get bigger and bigger in fixed proportion. Okay.
Was that what you meant when you mentioned coarse graining?
No, no, no. No, coarse graining is an entirely different thing. Coarse graining is what happens when you look at the world through through somebody else's glasses.
Question. If
Yeah.
you're trying to maximize C, then it's n log n minus the sigma of the denominator. Now, shouldn't we be minimizing the negative side of the equation?
Remember that this is positive. Yeah, you do want to minimize this thing.
Right. But that's what turns out.
No, well, yeah, you want to minimize this thing, but bring it back to this formula over here. In this formula over here, log p is always negative. So this is a positive quantity. You say, how did this go from being negative to positive? Well, when we subtracted off capital N log n, it works out. Yeah. So this is the entropy. This is the entropy. And what we have to do is maximize the entropy, but subject to constraints. All right, so this is getting a little complicated, but if we want to do it, we got to do it.
Excuse me.
If you don't want to see the scientific American version of it, but you want to see how it works, we have to do it. Yeah.
What's wrong with a simple, naive way of thinking about it? Just by symmetry, don't all the little ends have to equal each other? End of story?
If you don't constrain it by energy.
But that, where's the asymmetry coming from there? I don't understand it.
Because the energy of the different states,
Oh, yeah, okay.
yeah.
Yeah,
The energy
yeah,
of
I'm
this,
sorry.
yeah,
You're right.
yeah. All right, so our job then is to maximize this subject and to constraints. Maximize it with respect to what? Maximize it with respect to the choice of the probabilities. If we go back, we're maximizing it with respect to the possible occupation numbers. But that translates into maximizing the entropy. Remember, entropy has a value that depends on the probability distribution. And now we come to the conclusion that, that the most probable distribution of occupation numbers corresponds to probabilities which maximize the entropy. But maximize the entropy subject to constraints, and the two constraints are summation p sub I equals 1 and summation p sub I e sub I is equal to e. You imagine fixing the energy, fixing the average energy, and of course fixing the total probability set equal to 1, and look for the p sub i's which maximize the entropy. That's the rule. Okay. Does that make everybody happy? That you maximize, you find the probability for the ith state by maximizing the entropy given a certain total average amount of energy for the subsystem and given that the probabilities add up to 1. Okay. It's this one here which breaks the symmetry between the different states. That some have big energies, some have small energies. So we've reduced this now to a mathematics problem. Find the probability distribution find the probability distribution that gives you the maximum value for minus some p sub I log p sub I, given that summation p sub I is 1 and summation p sub I e sub I is some given energy E. To do this, we need a little more mathematics. We need one more mathematical concept to do it. The mathematical concept is called Lagrange multipliers. Lagrange multipliers come up over and over and over, both in probability, they come up in any problem where you're asked to maximize something subject to constraints. So I think we'll finish up the evening by talking about Lagrange multipliers, and the next time we will apply the method of Lagrange multipliers to exactly this problem. Many of the thermodynamic quantities, such as temperature, we will find that temperature is nothing but a Lagrange multiplier. So let's talk about Lagrange multipliers. I think this is a lot for one evening, but if we ever want to get to real statistical mechanics, we have to get through this, so let's do it. Okay, let's set this aside now. This is our mathematics problem. Write it down in your notebook. This is what we have to figure out. Maximize something with constraints.
Sorry, another question. Just to make sure I've got this. So we've got these states I, and then any given state has an energy EI. These are all givens. And then we want to maximize this based on that we want the probabilities times the energies to equal a given energy. That is.
You should really think of it as an average energy. We have capital N replicas, and presumably the whole thing has a given energy. But the energy is constantly fluctuating back and forth in such a way that the average energy in each one of these is the total energy divided by N. So the thing that I called E is the total energy divided by N. Right. Okay. So let's take up a mathematics problem. Given a function, f, of a set of coordinates, xi, these coordinates are really going to be the probabilities, but for the moment, let's just think of it as an abstract function, which is a function of some set of x's. We'll work out one or two cases with 2 x's and 3 x's, but all right. Problem: maximize f. Find the stationary point of, find the x's which make this function maximum. All right, now that's easy. We know how to do that. We solve the equations. Partial of f with respect to x1 equals 0, with respect to x2 equals 0, dot, dot, dot. This gives us an equation for each x, and we solve them simultaneously, and that tells us the solution. But we want to add something now. We want to maximize it. No, let's draw a picture first. This is the set of x's. This is the case where there are only 2 x's. Let's say x and y. And I can draw the contours of f. Let's draw the contours of f. Everybody know what I mean by the contours? The contour map. The level surfaces of the function. And typically a stationary point is usually a point, well, if it's a minimum or maximum, it always appears as a point which is surrounded by circles, so to speak. Not circles, but closed contours. So if somebody shows you the contour map and you want to find the extremal points, positive and negative, just look for the places that are surrounded by, well, you know what this says. If I have a mountain and I slice it by level surfaces, the peaks of the mountain look like little circles, and also the valleys also look like little circles. Okay, so that's where the maximum of the function is, where the circle occurs here. But now, these are the level surfaces of f. But now let's add some constraints. Let's add one constraint. What is one? We have two constraints in the problem we're interested in, but let's add one constraint. The constraint is we're going to look for the place where f is maximum, but given that something else is true. And that something else is that g of x is equal to 0, where g is some other function.
What is x? You only have x and y, sorry.
Yeah, g of x sub I, g of all the x's. Some other function is equal to 0. Now what if the other function is equal to 3? Well, then just subtract off the 3 and you can always, whatever the constraint is, you can always say that it's some function equals 0. Yep. So here's the constraint. And for example, the constraint equation, g of x equals 0, might correspond to some curve on here. Some curve, and now what we're looking for is along this curve, where is the function f? This is the curve g equals 0. And along this curve, we're going to look at f. F is one thing here, another thing here, another thing here, another thing here. And we're going to ask, where is f maximum along the constrained surface? Okay. Well, the first thing is that it will always be at a point where the level surface of f happens to be tangent to g. You can see why that is. That's not too hard to see, but it's not the important point here. Okay, so that's what we want to find. We want to find a tool, a trick for solving the constrained minimization or the constrained maximization in this case. So here's what we do. Here's the solution if we only knew how to find it. That's the place where f reaches its maximum value on the line g equals 0. Let's draw a contour now. Whoops. Which passes through here and which is perpendicular to the level surfaces of f. Perpendicular, it's a sort of steepest descent. It's the direction you move in on the side of the mountain to fall off most rapidly. All right, so you take that surface like that, and you look at the value along here. What's varying as you move from here to here? G is moving G is varying. Let's draw the different G's. Here's G equals 0. Someplace else, G is something, G equals 1. Someplace else, G is equal to -1, -1, and so forth. And let's look, as we move along here, let's look at f. As we move along here, is f going to be maximum at that point? No, not particularly. F is not going to be maximum along that point, unless by accident. This is not the place where f is maximum unless we also remember that we want g to be equal to 0. But if we forget g equals 0 and we move along here, then f has some shape. Let's plot f, and let's plot f against g. G is changing as we move along here. And as we move along, f is also changing. So f is some function along here. Let's give it a little more curvature. But this is g equals 0 right over here, g equals 0 on this line. But f is not stationary at this point as we vary g. F is not stationary. Why should it be? We're not looking for the place where f is stationary by itself. We're looking where f is stationary subject to the fact that it's living on this line. okay, what can we do to change this curve so that we actually make this point a true stationary point? All we have to do is add to f something proportional to g. Why is that? Is this obvious or not?
Derivative to, for the derivative to cancel?
Yeah. Yeah. There's a derivative over here of f with respect to g as you move along there. And if you add something proportional to g, with the appropriate choice, you can make this slope 0. Okay? If you add to a function like this something proportional, something linear in g, you can cancel this derivative and make it flat at this point. So by appropriate choice of adding something proportional to g, you can actually make this point a minimum of a new function. The new function is f, let's call it f prime. F prime is equal to f plus something proportional to g. Now, this lambda is a number. It's a number which is chosen to make the derivative flat here. I don't know what it is. I'll figure it out later. Let's put that question off for a while, leave it till later, but add something proportional to g, suitably chosen, so that this curve, which does not have a stationary point over here, is shifted so that it does have a stationary point. In other words, the statement is, if you take f and you add to it some multiple of g, then there's some value of lambda, some value that you'll determine later, which will make this whole function here stationary at exactly the point you're looking for. This is due to Lagrange. It's the method of Lagrange multipliers. Lambda is called a Lagrange multiplier. It's a devilishly clever trick. And I'm going to show you some examples. But first, before we talk about examples, let's ask, we've added another unknown into the problem. Originally, we had a collection of x's that we were trying to determine. We were trying to determine them by some set of equations like this. But we've now added another unknown, namely the value of lambda that will make f prime, or that will make that'll make f prime stationary at just the right point. Okay. So we have another unknown. But we also have another equation. What is the other equation? G equals 0. That was the whole point, right? The whole point was to maximize the function subject to g equals 0. So all we do, this is the standard method, we add something proportional to g, we minimize this, and then later we choose lambda so that the constraint is actually satisfied. I'm going to show you an example of it. If you haven't followed the details of this, go back and learn about Lagrange multipliers, but the machinery of doing it is very easy. I'll give you an example or two of how to minimize or maximize. Of course, it depends on the sign of the function, but that's not the important thing. Supposing, let's take a simple function, x squared. A second ago, this one. Let's take x squared plus y squared. And I always like to put a factor of 2 downstairs. You know why? Because I'm going to differentiate it. And every time I differentiate an x squared, I get a 2x. And I always prefer to put a 2 downstairs. That's not important. All right, I want to minimize this function. Can you minimize this function? I know exactly where the minimum is. It's at x equals 0 and y equals 0, right? But I want to minimize it given that x plus y equals 1. All right, so let's just draw the picture. This is f. So f is equal to x squared plus y squared over 2. And what is g? G is equal to x plus y minus 1, right? F is x squared plus y squared over 2. G is x plus y minus 1. We're seeking to minimize f subject to the constraint that g is equal to 0. All right, so the method of Lagrange multipliers tells us, let's first draw a picture. The contours of f are circles in this case, right? The constraint surface, so the constraint line, is x plus y equals 1. Where is x plus y equals 1? Here's 1, here's 1. X plus y equals 1 is a line like that. We're looking for the place along this line where x squared plus y squared is equal to 1. Where x squared plus y squared is minimized. By inspection, you can sort of guess where it is. You know, we can make it a little harder by, we can make it harder by making it 2x plus y is equal to 1, but leave it this way. Let's just check. All right, so what's the rule? The rule is add to f lambda times g. Let's do that. F prime is equal to x squared plus y squared over 2 plus lambda times x plus y minus 1. This is f, and this is lambda times g. Next step, thinking of lambda as a known thing, it's not known, but thinking of it as a known thing, minimize f prime. That's the rule. All right, so that means instead of writing df by dx is equal to 0, we write df prime by dx is equal to 0. And likewise for y. Let's see what we get. All right, the derivative of f prime with respect to x is equal to x from here, and then plus lambda, right? The derivative of f prime with respect to y is equal to y plus lambda. Now, what are we supposed to do with these things? We're supposed to set them equal to 0. That's the process of minimizing f prime, setting these derivatives equal to 0. So that tells us that x is equal to minus lambda and y is equal to minus lambda. X equals minus lambda and y equals minus lambda. Well, we found out one piece of information, incidentally. We found out that the solution, at least we know one thing, that x is equal to y. But so far we don't know what x and y is. What do we do next? We add the one more equation that g is equal to 0, and that's just the equation that x plus y is equal to 1. So x plus y is equal to 1. What does that give us for lambda? Minus 2 lambda is equal to 1, or lambda is equal to minus a half. Given that lambda is minus a half, we now know that the solution is x equals plus a half and y equals plus a half. In other words, right over here. That's the point which minimizes, minimizes x squared plus y squared, given that you're along this line someplace. So that's the trick of Lagrange multipliers. What happens if you have more variables and more constraints? Let's suppose you had 3 variables. I'm not going to work out the example, but let's suppose you had a function of several variables. Instead of just one constraint, you had several constraints. Well, then the rule is very similar. For each constraint can be written as g sub I equals 0. Let's say there are 2 constraints. g1 equals 0 and g2 equals 0. I'll give you a problem, a homework problem to work out using Lagrange multipliers. F is a function of 3 variables. It happens to be x squared plus y squared minus z squared. G1, the first constraint, is that x plus y is equal to 1. We've done that. We've done something like that. And the other constraint, G2, is that, I don't know, let's take it y squared plus z squared is equal to 7. I don't know, some ridiculous constraint. We want to find the minimum of f subject to 2 constraints that these two, let's make it simpler. I don't want to drive you crazy. Let's just make it z plus x equals 0 equals 1. 2 constraints. 2 constraints, find the place where f is minimum given that both of these equations are true. There is a place, you can find it, and the way that you find it is you add to f a Lagrange multiplier for each constraint. You call that f prime. And then you minimize f prime, pretending that you knew what the lambdas were. So you write derivative of f prime with respect to xi for all the i's is equal to 0. But you still have unknowns, 2 unknowns that you haven't specified yet, lambda 1 and lambda 2. What are the equations that govern lambda 1 and lambda 2? g1 equals 0 and g2 equals 0. Now you have enough equations to completely solve the problem. This seems like a rather complicated thing to do, but it is by far the easiest way to minimize something or maximize it when you have constraints. Why are we interested in it? Because in many problems in statistical mechanics, we want to maximize the entropy subject to some constraints. The constraints might be that the total electric charge has some value, the total energy has some value, total something else has some value. Those are the kinds of constraints that we impose. In particular, that the total energy is fixed, then, and the total probabilities add to 1. Those are 2 constraints. And so let's now write the mathematics problem. We wrote it before. And you can spend a little bit of time trying to solve it. I'll solve it next time. F, what is it a function of now? It's a function of all of the probabilities, P of I. P of I. It's a function of P1, P2, dot, 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 dot. Whole bunch of probabilities. It's a lot of variables. What are the constraints? The constraints are G1 is equal to the summation over I, P sub I minus 1. In other words, the constraint is G1 is equal to 0, or the summation of P sub I is equal to 1. And the other constraint is summation over I, P sub I, E sub I is equal to a fixed number E. the average energy. Given the average energy, and given that the total probabilities add up to 1, problem, maximize f as a function of all of the probabilities. What does that give you? That gives you the probability distribution as a function of I that corresponds to the most likely possible values for the occupation numbers. The occupation numbers tend to cluster around these values. This is not easy, but once you have the rules, once you know the rules, the rest is pretty straightforward. Okay, so incidentally, all of this, if you ask what branch of mathematics are we doing? The branch of mathematics is just probability theory. These same set of rules would govern many, many probabilistic problems. And we're not doing the theory of gases. We're not doing the theory of superconductors. We're doing basic probabilistic theory of maximizing some entropy, number of ways of rearranging things, subject to some constraints. The total amount of this or that is equal to something fixed. All right, so it's not special to any particular kind of physical system. It's special, well, it is special to the kinds of physical systems which have so many degrees of freedom that you are forced to deal with them statistically and probabilistically. But once you know that, the rules are always the same. Okay, so next time we will solve this problem. What is f? I didn't write what f was. F, I lost my, right, here it is. F is the entropy. We should call it S. S of P I, which is equal to summation over I, P sub I log P sub I with a minus sign. Maximize this. What are you going to vary? What are the variables that you're going to shift around to maximize it? The PIs. In other words, you have a probability distribution, and you're going to vary the probability distribution until you find that probability distribution, PI, which maximizes the entropy, given that the sum of all the probabilities is 1 and that the average energy is E. That's it. That's all of statistical mechanics in a nutshell. Solving that problem for different systems. Okay.
For more, please visit us at stanford.edu.